unable to attend. And I will share my screen. Okay, so today is Wednesday, March 22nd of 2023, and I wanted to begin to see if perhaps you have questions related to our discussion on Monday about the normal distribution. I don't know if you've had an opportunity to look at quiz number 4, which is over the normal distribution.
I didn't look over the quiz.
Okay. Okay, so let me remind you that quiz 4, which does cover normal distributions, is due by Sunday. Also, today we're going to talk about the central limit theorem, and that is quiz 5. And so quiz 5 is also due by Sunday. So you have 2 quizzes that are due by Sunday, which is March 26th. Do you have questions about anything else to date? Anything that we've covered up to this point that I can try to clarify before we jump into the central limit theorem?
No questions.
Okay, I am using the PowerPoint for the central limit theorem. Okay, again, if you go to the course homepage in D2L, we are under Module 2. And today our topic is the central limit theorem applications. And I'm going to use the PowerPoint that is available in that lesson. So the central limit theorem we abbreviate it. Sometimes you'll hear me say, or you'll see me write CLT, which is just the shorthand notation for central limit theorem. And guys, it is one of the most powerful and useful tools in all of statistics. I was looking this morning, it was actually introduced by a mathematician, French mathematician, de Moivre, in 1733. It was not well received and kind of was quickly forgotten about, and then was reintroduced in 1812 by Simon Laplace. So it's been around for a long time. And it is, again, one of the most powerful tools that we use in all of statistics. Because if we can know what type distribution we have, or even if that distribution is unknown, knowing that our data behaves or in a predictable way is very powerful. That also can help us to identify what type of analyses we can and cannot do for our data set. I did mention it's abbreviated oftentimes CLT, central limit theorem. Basically, in everyday terms that hopefully you can understand, the central limit theorem forces any distribution, whether it's a binomial distribution, a uniform distribution, an exponential distribution, any distribution, even if I don't know what distribution it is, even if it's, an unknown distribution, the central limit theorem forces it to be normal. If I choose, I've got the hiccups, to be it forces it to be normal if I have a large enough sample. Now, there's debate on what does that mean to have a large enough sample. Okay. Typically for us, that's around 30. Okay. But it doesn't have to be 30. Could be less. And so again, knowing that I can take any distribution, even one that I don't know what the shape is, and I can force it to be normal, which then means I can apply all of the information that I learned about a normal distribution that we actually talked about on Monday and apply it. We get that idea of it being bell-shaped and continuous and symmetric about its mean. And then we can use those techniques that we talked about on Monday to solve problems. There are two versions, or what is often called alternative forms, of the central limit theorem. One of them looks at it from a perspective of the mean. The other looks at it from the perspective of the sum. And sum typically means that you're going to add things together. So we're going to explore for just a little bit, and I don't normally do a lot of the theory behind these, but this is just a really neat tool or a neat guideline that we use in statistics. And a lot of times it goes on behind the scenes and we don't think about it, but it's really neat to see. So I want to kind of show it to you. And we're going to focus first on the version for the mean. So this is the central limit theorem for mean. And it says, if we collect samples of size n with, again, a large enough n from an unknown distribution and calculate each sample's mean and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. I'm going to show this to you in just a minute. Now, again, there's a debate about what size, the size of the sample n that's required to be, quote, large enough. Again, we tend to say it needs to be 30 or more, okay? Or you have to know that your data comes from a normal distribution originally. If your population is very, very different from being a normal bell-shaped symmetric distribution, then we may need more than 30. And just as a side note, that sampling is done with replacement, meaning I select a group, put it back into the mix, select another group, put it back into the mix. That's what it means to say sampling is done with replacement. I'm always returning the group back before. So you could have, you know, a person or an object that's selected multiple times within different groups. And again, the result, and I'm going to tell you the result, and then I'm going to show it to you because it's really neat. I'm sure you probably don't care, but it is kind of neat to see. So we're saying if, regardless of what kind of distribution I start with, if I collect enough samples of size n and I create the picture, that resulting picture should be a normal distribution. And what's neat is the mean of the central limit theorem distribution is the same as the mean of the original distribution. And then the standard deviation of the central limit theorem is actually slightly lower. Okay, let me make you a little note here. And notice these symbols out here. You'll see this notation. You'll see mu, which is our symbol for the mean, and you'll see a little subscript with an X bar. That is how we represent the mean of the central limit theorem. That little subscript of X bar lets me know that we've applied or used the central limit theorem. But again, what's neat is that the original distribution, the mean of the original, is the same as the one for the central limit theorem. It doesn't change. For the standard deviation of the central limit theorem is slightly lower than the original distribution. And the relationship between the standard deviation of the central limit theorem, and again, the symbol there is you have sigma, which is our standard deviation symbol, and you have that subscript of x bar. Again, that lets me know that we've applied the central limit theorem. So whenever you see that notation, that lets you know that we've applied the central limit theorem and we've applied the version related to the means. But typically the standard deviation for the central limit distribution is lower. And if you think about it, that should make sense. Because if I look at one item or one person in comparison to thousands or hundreds of thousands, that one item or one person could be really different from everybody else. But if instead I looked, say, at 5 people or 10 people, and I looked at a group, that group is going to tend to vary less than one individual. Okay? And I want to kind of prove this to you. I don't want you just to take my word for it. Okay? So here's what I did. Okay, here's kind of the proof. Years ago, I had access to students' social security numbers prior to the use of ID numbers that we now have, the Georgia Highlands College ID numbers. So everybody, or most everyone within the United States, has a social security number. That's how the government tracks us. Our social security numbers are made up of 9 digits. The first 3 digits are what they call an area number, and it's assigned to a geographical region. So, you know, the South has an area number, the Northeast has an area number, the Midwest may have an area number. So the first 3 digits are based on the area of the country, of the United States at least, the area of the United States in which you were born. The second 2 digits are what they call a group number. And that has to do something with even and odds that are allocated to a specific area or region of a state. So you go from having a region of the country to a region or an area of the state. That's the middle 2 numbers. And then the last 4 digits of your social security number is called the serial number, and they are supposed to be assigned randomly. Okay? And so we're going to look at those last 4 digits and to think about, are they really truly assigned randomly? So again, I collected the last 4 digits of the social security number for 131 people. Okay, I had access to students, so the students that were enrolled in my courses for the semester that I was collecting data, I collected the last 4 digits of their social. So I have 131 people, and from each person, I collected the last 4 digits. So for example, if I came up and if I wanted to include myself, the last 4 digits of my social are 6275. I could include my husband. His last 4 digits are 6386. My daughter is 1901. Okay, so I collected the last 4 digits for 131 different people. If we look at the graph of those 4 digits individually, and I had them in individual columns, so like the blue that you can see a little bit of would be the first digit, so that'd be like my 6. This would be like my 6, 2, 2.75. Okay, so then the pink was the second, the yellow was the third, and green was the fourth. So if I graph all of those four numbers individually and create a histogram, look at the shape that we get. Now, it's not perfect, but it's pretty doggone close. Whoops, a little crooked there, sorry. But it's pretty close to being a uniform distribution. Which does tell me, by the way, that they are probably randomly assigned. The fact that that turns out to be a uniform distribution. If I took all 131 numbers, added them together, and divided by 524, because you had 131 people, four numbers each, that gives me a total of 524. If I add those 524 numbers together and divide by 524, my mean was 4.45229. And the standard deviation was 2.897156. I took all of those 524 numbers, put them into Minitab, and I created the histogram, and I calculated the mean and the standard deviation. So initially, we have a uniform distribution. If I look at each individual data value as an individual, okay, we have a uniform distribution. Now, if I take those same sets of numbers, and instead of looking at them individually, I look at them as a group. So I would take my group would be 6, 2, 7, 5, and I average it. Okay, so 6 plus 2 is 8, plus 7 is 15, plus 5 is 20. So I would have 20 divided by 4. The average for my Social Security set of four numbers is 5. If I did that for my daughters, we would have 11 divided by 4. That would be, I believe, 2.75. Okay, so instead of looking at them as an individual number, we look at them as a group of 4. So I'm looking at a group. And if I do that for all 131 that I have, look what happens when we graph the distribution of those averages. Okay, keep in mind that the individual values are uniform. When I graph the mean of each one, whoops, sorry, got ahead of myself. Look at the shape of the distribution. When I took each of those 4 digits and found the average, look at the shape of the distribution. And notice that that shape now is approximately normal. So we took a uniform distribution, and by looking at groups of numbers instead of individuals, we have forced the distribution to be normal. And because now I have a normal distribution, I can do all those things that I know how to do with a normal distribution. If I took the mean, basically I do the mean of the means. Once we find 6, let me get over here where you can see me. 6, 2, 7, 5, and we calculated the mean to be 5. The mean of my daughters was 2.75. and then I take the average or the mean of those means, guys, look what we get. We get 4.45229. The standard deviation of the central limit theorem is 1.475803. Let's look at them side by side. Our original distribution, remember, was uniform. The central limit theorem distribution is normal. And I told you a while ago that one of the consequences of applying the central limit theorem is that the mean of the original was the same as the mean of the central limit theorem. And look, lo and behold, we get exactly the same value. Now, I mentioned that the standard deviation for the central limit theorem is slightly lower than it is for the original, and you can see that they're not the same value, and the standard deviation of the central limit theorem is lower. Now, if we actually use the numbers, okay, the rule says that the central limit theorem standard deviation is the original divided by the square root of n, where n is your how many people are in the group. So in number form, that would be 2.897156 divided by the square root of 4, because we had groups of 4. So that's 2.897156 divided by 2. And if I get my calculator, and let me grab mine, we would have 2.897156 divided by 2, which gives me 1.448578. So using the formula, I get a slightly different number than what I got when I used the raw data. But guys, I'm pretty close. I'm in the ballpark. The values for the central limit theorem are estimations or a little bit of approximation, but I'm pretty doggone close. So the central limit theorem, it is beautiful because we can take any distribution, and we can force it to be normal, where we have the mean is the same as the original, and the standard deviation is basically what I call adjusted, and it's going to be slightly lower. And then we can use all of the stuff that we've learned about the normal distribution. And the normal distribution I mentioned to you on Monday is one of the most used and most useful distributions in all of statistics. Okay, so let's take a look at an example of how this would work. And again, I've moved this over to the Word document so that we can work through the problems together. Okay, so the first example related to central limit theorem of the mean says, the length of time taken on the SAT for a group of students has an unknown distribution with a mean of 3.5 hours and a standard deviation of 1.25 hours. A sample size of n equals 100 is drawn randomly from the population. Now, a couple of things, a couple of clues that you need to apply the central limit theorem. First of all, in this scenario, it tells us we have an unknown distribution. So if you think about it, up to this point, we've talked about the generic discrete probability distribution, the binomial probability distribution, the uniform probability distribution, the exponential probability distribution, and the normal probability distribution. We haven't talked about an unknown one. Okay. It also tells me that I'm going to draw a sample size of n equals 100, not just 1 or A. Remember, I kept pointing out Monday that in all of the examples that we looked at Monday, it wanted us to select a randomly selected student or a randomly selected item. They wanted us to select just one. Well, in this scenario, we're going to select 100. So the fact that I have an unknown distribution and that I'm going to select a group, not just one, is my clue that I want to apply the central limit theorem. Okay. So that's my clue. Those are my clues that I want to apply the central limit theorem. So when I go to apply the central limit theorem, I need to determine what my mean and my standard deviation are going to be for the central limit theorem. So finding the mean, remember, of the central limit theorem is the same as the mean of the original, which is given in the problem. So the mean here is 3.5 hours. That's given in the problem. Then it says, what is the standard deviation you will use for this problem when looking at the average of the 100 people? Again, this phrase lets me know that I want to apply the central limit theorem. It is also very important that you round as they indicate, because using that value in your calculations, it needs to be rounded as stated, because that's how you're going to match the answers that you're going to find in your homework quiz, on your homework quiz. So again, we know that the standard deviation for the central limit theorem is the original divided by the square root of n. The original is given to us in the problem and is 1.25. And our sample size is 100. So I have 1.25, square root of 100 is 10. 1.25 divided by 10 would be 0.125. So the standard deviation that I would use is going to be 0.125. The way these questions are worded, it's going to say, find the probability that the sample mean. Okay, before, if you go back and look at the lesson on Monday, and let me see if I can pull those up so you can see the difference. Maybe I can pull those notes up. Okay, notice how these questions say, find the probability that a randomly selected student. They're just asking you to outright find the probability. Today, they ask you to find the probability that the sample mean. Okay, so again, that phrase that you're trying to find the probability of the sample mean is another clue that you're going to apply the central limit theorem. So for these problems, and I'm going to make a notation here, for these problems, we're saying that our variable is now approximately normal with a mean of 3.5 and a standard deviation of 0.125. Okay, I have applied the central limit theorem. So based on the central limit theorem, my mean corresponds to the mean that's given in the problem. My standard deviation has been adjusted, and I'm going to use it. Okay, you've got to be able to identify that you need to use or apply the central limit theorem. Beyond that, because we know we have a normal distribution, we're going to basically do the same thing we were doing on Monday. And again, I like to draw the picture. So this one says find the probability that the sample mean is between 3.25 and 3.75. Okay, so I have a normal distribution. I now know that it's normal. Originally, it was unknown, but because I've applied the central limit theorem, I now know that it is normal. The mean is 3.5. I want to consider being between 3.25. So I have 3.25 and 3.75. Between. So we're looking for the area under the curve, which corresponds to the probability. Remember, Minitab uses the phrase middle. Okay, so we're using the same guidelines or the same clicks, if you will, that we used on Monday. Because we're still dealing with a normal distribution, but what has changed is I have applied the central limit theorem. So I'm going out to Minitab. It's probably gone to sleep, so I'll have to wake it up. Giving it just a minute to wake it up. Again, you're going to use the same keystrokes as Monday for the normal distribution. So if you'll recall, that is stat. No, wait, excuse me, sorry. Graph. Probability distribution plot. We have one curve, and we want to view the probability. You have to double click. Doo-doo. We do now know we have a normal distribution since we've applied the central limit theorem. The mean of the central limit theorem is 3.5. The standard deviation of the central limit theorem is 0.125. Options. We have a specified X value. We are between or in the middle of 3.25 and 3.75. And I click OK. And I click OK. And it does give us the graph. And I'm going to copy the graph over to our paper. Come on. Okay. So here's your picture. Again, what you're looking for is this number that's hanging out in space above this red shaded region. Is 0.9545. So this red shaded region is 0.9545. And again, D2L likes that leading zero, so you should put 0.9545. So what we're saying is the probability that the sample mean, see, what was our variable? Taking the SAT. Mean time to take the SAT is between 3.25 hours and 3.75 hours is 0.9545 or 95.45%. Okay, remember this number that we're getting from Minitab is a decimal, and it's acceptable. I can convert it to a percentage. Remember, you take the decimal value times 100%. And the way you express your answer is typically dependent upon the verbiage or the wording of the question. This one asks for probability, and so the decimal value is acceptable. We're basically doing the same thing that we talked about on Monday with a twist. And the twist is the central limit theorem. Okay, so let's look at this next one. Same scenario, so we know that the length of time taken on the SAT for a group of students has an unknown distribution, but we have forced it to be normal by applying the central limit theorem. Okay, so I still know here that my variable is approximately normal with a mean of 3.5 and a standard deviation of 0.125 because I have applied the central limit theorem and forced that unknown distribution to be normal. So again, I'm going to draw a picture. So I have my horizontal number line, my normal bell-shaped distribution with my mean in the middle, which is 3.5. This question says less than 3.6 hours. So 3.6 hours, and I want to be less than. Well, notice this less than is to the left. So I'm looking for the area of this red shaded region. This would be a left tail. And again, I can apply or use the normal distribution because of the central limit theorem. So I'm going back to Minitab. Graph, probability distribution plot, one curve, view probability, 2 clicks, 1, 2. It is normal. My mean is 3.5 for the central limit theorem. My standard deviation when I apply the central limit theorem is 0.125. Options, I want to be less than 3.60. And I click OK. And I click OK. And again, you get this graph. Okay, so again, what you're looking for is this number that's kind of hanging out above the red shaded region, which is 0.7881. So this red shaded region is 0.7881. And again, that's going to be the value that you enter as your answer. Again, I keep stressing this, D2L wants to see that leading zero, 0.7881. Now, again, what that means in this context is that the sample mean time to take the SAT has, oh goodness, I said it all wrong, I'm sorry. The probability that the sample mean time to take the SAT is less than 3.6 hours is 0.781, or as a percentage would be 78.81%. Because it's really not anything new. We're still doing a normal distribution, but we have the twist of applying the central limit theorem because the original distribution was not normal. Okay, one more. Again, we still know in this scenario that because we've applied the central limit theorem, that our variable is approximately normal with a mean of 3.5 and a standard deviation of 0.125. Okay, and this time we want to know that we're greater than 3.15 hours. So visually, I'm going to draw my horizontal axis. I know that my distribution is normal because of the central limit theorem. The mean is 3.5. I want to know the probability I'm greater than 3.15. Greater than is going to be to the right. So we're looking for this red shaded region to the right of 3.15. Because we're to the right, this is called a right tail. Going out to Minitab. Graph, probability distribution plot, one curve, view probability. Doo-doo. It's normal. My mean is 3.5. My standard deviation is 0.125. Options, we want to be greater, right tail, than 3.15. Click OK. Click OK. And I'm going to copy the graph. And again, what you're looking for is this value that's kind of hanging out in space above the red shaded area, which is 0.9974. So this red shaded region is 0.9974. And again, that would be what you enter as your answer. Now, again, thinking about what that means the probability the sample mean time to take the SAT is greater than 3.15 hours is 0.9974 or 99.74%. Now, do you have questions related to what we're doing? Do you have questions about the central limit theorem or questions about the normal distribution before we move on?
No question.
Okay, thank you, ma'am. All right, so we're going to move on and we're going to look at the second version of the central limit theorem. Remember, I told you there were two approaches or two alternative versions. The first one deals with the mean, and quite honestly, that is the version that I have seen used most often, that I probably learned. I am not overly familiar with, and I don't recall ever seeing the second version used, but you need to be aware that it exists because there might be some scenarios. Again, I just don't recall through all the years of my experience using or seeing this particular version. That doesn't mean it's not used. It just means I've never run across it. Okay, so version 2 for the central limit theorem is related to the sum of the values. So again, what it says, I've got hung up. So I have to stop the share and then go out and exit out. Give me just a second. It does this weird stuff every now and then. Let me share my screen again. Okay, so the central limit theorem for the sum, it basically says the same thing. It says if we collect samples of size n with a large enough n from an unknown distribution, and we calculate each sample's sum, instead of averaging them together, for example, if you were using my digits 6275, we would find the sum, which means we would add them together. Okay, we just do the addition and we would get 20. We do my daughters, we would get 11. If we did my guys, listen, my power is blinking on and off. Hey guys, are y'all still there? Nana? Hello? Are y'all still there? Nana, can y'all hear me?